Hi. In class this week, we talked about contextual analysis and all the reasons why linear regression analysis might not be the best model for data that have a hierarchical structure. What we didn't discuss yet is actually why it is or what it is that we can use as an alternative. And that's what I want to do in this video. And what I want to present here is the hierarchical linear model, and we're going to build this up very slowly, starting with the random effects analysis of variance model that we actually discussed in class, and then all the way up to a more complex model down the line. And we'll do this using the example of generalized social trust from the paper by Mark Hoge and his co-authors. So first notation, what we're going to do is we're going to look at individual I's level of social trust in country C. We're going to call that Y sub IC. So we're going to assume that these individuals are nested inside one and only one country each. We're going to look at only two predictor variables in this very simple setup. The first of these is an individual level attribute, and that is the individual's level of political efficacy. I'm going to write that as X sub IC. And the second variable is actually a measure of the ethnic diversity in country C, and I'm calling that Z sub C. Now, the very simplest model that we can come up with is basically a model that simply decomposes the trust score of individual I in country C into a couple of components. And that's what we're going to do, and that is essentially the random effects analysis of variance model. So what are those components? Well, the first component is a grand mean. We call that a grand mean because it's the expected level of trust across all countries and all individuals. So if we would randomly select a country and then randomly select an individual from that country, we would expect to see a trust level that is equal to the grand mean. And a little bit in deviance of the notation I showed on Monday, we're going to denote that grand mean by gamma sub 0, 0. That's a notation that will become more apparent as we keep going today. Now, to that grand mean, we can add a country level error, which is the deviation of the expected trust in country C relative to the grand mean, and we call that delta 0C. So what that country level error takes into account is that in a specific country, say Switzerland, the level of trust may be higher or it may be lower. In fact, it's higher than the grand mean. Then we add to that as well an individual level error. That's the deviation of respondent I's trust level relative to the country mean, and I'm going to denote that by epsilon sub IC. We know that it's an individual level characteristic because it has both a subscript I and a subscript C. And what that individual level recognizes is that actually some individual score may also be larger or smaller than the average in the country in which that individual resides. So basically, what we're actually now getting is that the final score that we observe has to do with something that is in common to all countries and all individuals, something that is specific to the country in which we observe the individual, plus something that is specific to the individual. We can actually very nicely illustrate that here, and in the process we actually derive a model that we can then estimate. So what I've done here is I've depicted in this picture here the grand mean as estimated from the European Social Survey data. and that lies around 5. It's a bit higher than 5. And then I have added here also, that's the light green arrow that you see, the mean that we observe in Denmark. That DK that you see in the picture stands for Denmark. And what you see there is also that I called that mean for Denmark beta 0C. The difference between beta 0C and gamma 00, the grand mean, that is delta 0C. That's what you see depicted underneath the horizontal axis. And in this case, the average in Denmark is higher than the grand mean. Danish people are more trusting of other people than the average in the European Social Survey. And so in this particular example, delta 0C, the level 1 error, the error that pertains to the country level, is actually a positive number. Now, I've also depicted here a particular respondent from Denmark, and that respondent has a score of YIC on trust. In this case, I've picked the respondents with a score of 9 on the trust scale. And of course, that respondent is even more trusting of other people than the average respondent in Denmark. And the average respondent in Denmark, of course, we've already seen is more trusting than the average across the countries that we're studying. And so what we're seeing here is that this deviation of the respondent from the Denmark country mean, we call that epsilon IC. And you see easily that if I take delta 0C and I add to that epsilon IC and I add all of that to the grand mean, then I get the score YIC that I observe for this respondent. So what we can do is we can actually formulate what is in this picture in terms of 2 equations, what we call a level 1 model and a level 2 model. The level 1 model here is always defined in terms of the response. So the response here is Y for individual I in country C. And we're going to say that that is equal to a mean that is specific to that country, beta 0C, plus an individual level, a respondent level deviation from that mean, which we call epsilon sub IC. In the picture, that epsilon sub IC is positive, but it could of course also be negative. We could have found someone in Denmark who is less trusting than the average Danish person. So what we're saying is that these epsilons actually, they vary, and we're going to assume, and that is typical of hierarchical linear models, that the epsilon is drawn from a normal distribution with a mean of 0 and a standard deviation of sigma. So that's the level 1 model. The level 2 model is a little bit strange looking perhaps, because what is on the left-hand side of that model equation is not a random variable, but a coefficient, beta 0C, the mean in a particular country. And we are able to treat that as a stochastic variable because we're assuming that we're randomly sampling countries in this particular case. So beta 0C here is going to be written as a function of the grand mean, gamma 00, plus some deviation delta 0C that captures how much and in what direction the state mean, the country mean, deviates from the grand mean. In this particular case, the Danish mean exceeds the grand mean, but there are also cases where, like Greece, for example, where the country mean falls short of the grand mean. So these deltas, 0Cs, they can also be both positive and negative, and to capture that, we're going to assume that they too are draws from a normal distribution with a mean of 0 in this case and a standard deviation of the square root of tau 00. Now, we make some assumptions here. They are hidden a little bit, but it's important to note them. The first assumption that I've highlighted here is exchangeability. We are assuming that any country that we have observed in the data, in the European Social Survey that is, can be replaced with any other randomly selected country. So Denmark, which I showed on the previous page, could have been left out and replaced instead with a sample from, say, Romania. We don't have Romania in the data, but in theory that could have been exchanged for Denmark. The second assumption that we make here is that the level 1 and the level 2 errors are uncorrelated. So that's actually an important assumption as well, because it means effectively that we're actually assuming that the processes, that the sampling processes at the country level and at the individual level, they are distinctive processes. So let's see what we actually get when we estimate this random effects ANOVA model in our data. So here is what the data look like. And I basically just selected out a couple of variables that we will need for this exercise. There are more variables in the data, but I selected country, social trust, political efficacy, and a measure of the immigration flow, which is a relatively crude measure of ethnic diversity, truth be told, but it's the one that was easiest to find. Now the question is, what happens if we actually want to estimate this random effects ANOVA model? Well, we're going to do that, and you will practice that next week with Benny. We're going to do that using the package LME4. That is really one of the major linear modeling packages for hierarchical data. LME stands for linear mixed estimation, and that's what we're doing here. So I'm creating here an object that I've called ANOVA_fit, and that's going to be a linear mixed effects regression, an LMER. So it's a linear model that we're applying. And now comes the syntax. The key bits of syntax here are the equation specification and the details about the estimation. So I have no predictor variables in this random effects ANOVA model. The only thing I'm saying is that social trust is equal to a grand mean plus some deviations from that. So I can capture that by writing soc trust tilde 1. That's capturing the grand mean bit, plus opening parenthesis, then the constant bar country. 1 here is the constant, and bar country means that actually we're going to say, well, there is a grand mean, and then there is actually a set of country means, and the 1 bar country captures those country means. We don't actually have to specify anything about the level 1 errors, the respondent level errors. They are done for us automatically. You'll see that this syntax repeats itself, and you will have plenty of opportunity next week to practice this. The data we're going to use is work, which I created on the previous tab. And then there's a detail about estimation. REML equals true means that we're going to use restricted maximum likelihood. Don't worry too much about that detail yet. We will get to that later in this course. If you run this, then you get the following estimates. There's a lot of it, so you need to scroll down here. And the first bit I'm actually going to skip. I'm going to go to the section here that is called random effects. and then I'm going to the section here that is fixed effects. So if we actually look at the random effects, we see that there is a country level random effect and a residual random effect. And we get variance and standard deviation estimates. This 1.7701 that you get for the residual standard deviation, that is our estimate of the standard deviation of epsilon. So this is our estimate of sigma. If we square that, we get this 3.133. That is sigma squared, or the estimate of that. The value of 0.9514 that you see here for the country, that is our estimate of the square root of tau 00. And if you square that, you get to 0.9051, and that is the estimate of tau 00. So that is actually capturing how much variation there is across these country means in social trust. And what this 3.1332 captures is the variation we have at the individual level in levels of trust. Now, what about the grand means? So now we have some indication of what happens with the delta zero C's. In particular, what we have captured here is tau 00. We have some indication of what happens with the var epsilons. Particularly, we have an estimate here of the variance. But what about the estimate of the grand mean, which we also need? Well, that we get in the last portion of the output, the portion on fixed effects. And here you see a grand mean of 5.15 roughly. So that is our estimate of the average level of trust across all countries and all respondents. Trust is measured on a 0 to 10 scale, so we basically find here that on the average, the people are slightly more than the neutral point, one could say, on the trust scale. Now, one of the things we talked about last time is that there is some form of clustering. As soon as we have a non-zero value of tau 00, there is some degree of clustering happening. We've also talked about how the interclass correlation captures that. So let's calculate that interclass correlation. So for that, I use a different library, performance, and then I use the ICC command. And in fact, typically we get there two estimates, an adjusted and an unadjusted. They're the same in this particular setup. Usually that's not the case if we have more complex models, and I would recommend looking at the adjusted one in that situation. But what this number tells us here is that 22.4% of the variance in social trust comes from cross-national variation. So the fact that the country means are different. And the remaining 78% roughly comes from individual variation, the fact that individuals are different. So we've now accounted for the variance that we see in general social trust, because now we know, and we didn't know that before, that about 78% of that variance is across individuals, but a quite sizable 22% is across countries. But what we haven't done yet is try to come up with an explanation of why individuals vary in their trust, or why countries vary in their trust. That we're going to do in the next video.